So, the kinetic molecular theory accounts for the behavior of atoms and molecules. We've talked about this before. Kinetic means motion. Molecular means molecules. So we're explaining the motion of molecules. Just a quick recap. What's the difference between a theory and a law?
Is a law?
No! Whoa.
Jeez.
I mean,
Isn't it like a law has been experimented on a bunch of times?
Nope.
And then like, oh. Okay, hold on. So, law is about
I'm not going back.
Nope.
I got it. Okay, so a law.
hello.
Hi, I have yearbook slips for you to pass out.
Oh, okay. If you could just leave them on my desk.
Okay, like a law is something that has been tested and has been proven.
Bless you.
No. All right. Oh, go ahead.
A law states it, but the theory explains it.
Thank you.
Good job.
Yes. Good. All right. A law describes a relationship, usually mathematically. A theory explains why something happens. Right. So the kinetic molecular theory is an explanation. Right. It's based on the idea that particles of matter are always in motion. Right, so it helps us understand the properties of gases by providing a model for an ideal gas. Right, so an ideal gas is imaginary. It's just a theoretical concept. So it's an imaginary gas that perfectly obeys every single aspect of the kinetic molecular theory. Yes.
So if no gases obey it, doesn't mean it's like a false theory.
We have ways of accounting for how real gases don't follow. But we use this as a simple basis to kind of get the general idea. And then we start accounting for other things. So we're starting at the bottom and working our way up. So, all right, there are 5 tenets or postulates of the KMT. It's basically 5 statements that define the kinetic molecular theory and what ideal gases are. Right? So gases consist of molecules that are in constant motion. Just like when we played the amoeba game outside, you guys couldn't stop. Some of you did, but you can't do that. All right, the molecules of a gas are infinitely small particles that are far apart relative to their size. So the molecules of gas are infinitely small points, which means what about their volume? They occupy no volume.
Oh, okay.
Basically, I'm saying the gas is so small it doesn't have any volume. Again, this is an ideal imaginary gas. Right? So most of a gas is empty space. Right? So it's low density, highly compressible. So the third tenet is that molecules travel in straight lines until they collide.
Wait. Never.
So you travel in a straight line until you hit something else. So collisions can occur with other gas molecules or with the walls of the container. And these collisions are perfectly elastic. Right? So collisions are elastic. What that means is no energy is gained or lost during the collision. So you bounce back with the same amount of energy as what you hit with. So you're going at the same speed. There are no attractive or repulsive forces, so there's no intermolecular forces. So molecules only influence each other by hitting each other, by colliding. The average kinetic energy of the gas particles is directly proportional to the Kelvin temperature of the gas. So as temperature increases, so does kinetic energy. It's a direct relationship. Yeah, Millie.
This is sort of unrelated, but I feel like boiling boiling water and it becomes a gas and you like cool down the room and have condensation, will you not get the same amount of water you had before once you like condense it?
I mean, you should,
'Cause,
theoretically.
like, if a gas particle's in that corner of the room and you're like cooling the water down at that
Oh, I
corner.
see what you're saying. I mean, if the entire room was cooled down, then you should get the same amount. That's not going to happen. But theoretically it would. Alright, so that's the 5 tenets of the kinetic molecular theory. Okay, so I have a chart down here. Basically, I've put these points, right, to describe what is an ideal gas, and we can compare it to a real gas. Oh, wait, did I not get the last one? Oh, no, it's the same one. Okay, so all gases at the same temperature have the same average kinetic energy. Okay, so this is what's called the Maxwell-Boltzmann distribution. Right, it looks at the speed of particles, so the temperature, right, and the relative number of those molecules. So when you're hot, you have a higher speed. Right, when you're cold, you're moving slower. Right, that's because kinetic energy, when you go and take physics, it's 1/2 of the mass times the velocity, which is speed, squared. Right? So if you have more kinetic energy, you have a higher velocity, is what this is saying. This becomes really important as far as kinetics and other things if you take AP chemistry. Right now, the thing I want you to notice is the more kinetic energy, the higher the temperature, the higher the speed. So small particles are going to move faster than large molecules to get the same average kinetic energy at that temperature. Right? So if this is the same, right, if this is bigger, we have a lower velocity. If this is smaller, we have a higher velocity. Right? They're inversely related. Do we see that? Okay. So kinetic molecular theory describes ideal gas particles. So an ideal gas is assumed to have blank volume, zero volume, or no volume. It is in constant straight line motion. Straight line motion. What type of collisions does it experience? Elastic. So no energy is lost, no energy is gained. It has no attractive or repulsive forces, no IMFs. The average kinetic energy is proportional to Kelvin temperature. And most importantly, do they exist? No, they don't really exist. So then what's a real gas, right? It's still in constant motion. That part is still true. I think that's actually the second bullet. It is the second bullet. So that's one way real gases are actually ideal. They are in constant motion. Now the collisions are not elastic. So some of that energy is transferred when you hit something else. The particles have intermolecular forces, or attraction and repulsion. And the particles themselves take up space and have volume. The other way that real gases are ideal, their average kinetic energy is still directly proportional to Kelvin temperature. So the way these line up, right? You're in constant motion, kinetic energy is directly proportional to temperature. How do they not line up? All right. Ideal is elastic collisions. Real gases are inelastic or not elastic.
One has intermolecular forces.
Which one?
Real gas.
Real gases have intermolecular forces. Ideal gases do not. And there's one more.
real gases have volume?
Great. Real gases take up volume. Ideal gases are assumed to be so small they don't have any volume. All right. So our last thing about kinetic molecular theory is then why use ideal gases? So ideal gases simplify the model that we use to describe gas behavior. We're taking out variables. Now, although ideal gases don't exist, real gases can approach ideal gas behavior under certain conditions. So under certain conditions, you can have a real gas that's actually very close to behaving ideally. So this happens when you're moving really fast and when you're very spread apart. So what do I say about temperature? It's high, and volume is also high. So, gas behavior is most ideal at high volume, which is also low pressure. And we'll talk about how those two are related. And high temperature. Yes.
Wait, so why is it most ideal at high volume when an ideal gas is low volume? Or no volume?
Now, that's talking about the actual gas particle. Right? So I'm saying the particle is so small, it basically takes up no space.
Oh.
Not the space that it's moving in.
Oh.
It's a good question. All right. So after our last test, I learned that you guys really haven't nailed down standard pressure yet. Okay. So physical properties of gases. Standard pressure occurs at sea level. 1 atmosphere is 101.3 kilopascals, which is 760 millimeters of mercury and 760 torr. You need to know these conversions. Now, what is standard temperature? What is it in Celsius? It's 0, right? Which is what in Kelvin? 273 in Kelvin. Remember, you think about it this way, the standard temperature and pressure is the normal freezing point of water, 1 atmosphere and 0 degrees Celsius. That's going to be really important in this unit. So, the units of force pushing down on us, we talked about millimeters of mercury, looking at the barometer, and torr being Evangelista Torricelli. All right. So, density. The density of a gas is about 1/1000th. Okay. The density of the same substance as a liquid or a solid. Remember, we described solids and liquids as being condensed forms of matter. Gases are very much not condensed. Right? Because particles spread to fill their container, gases are mostly empty space, meaning they have a very low density. Yes?
So would fog be considered like a gas?
Fog is a gas.
It is a gas?
Yeah.
You can feel it. Like if you walk through it.
Have you ever had the wind blow on you?
Yeah.
That's a gas.
But it's like moist.
Because once it hits you, it condenses onto your skin as a liquid.
Okay, so like it does it really fast.
Sure. Water is wet.
Oh my god.
I mean, it is.
We're not bringing this back. No. Wait, she explained it.
Wait, can you explain?
Yeah,
Aristotle, man.
Aristotle
Classified
is
water as
crazy.
being cold and wet. Fire is hot and dry. Earth is cold and dry. And then what's the last one? Air. Air is hot and wet.
Yeah, but Aristotle got stuff wrong, so why is that right?
Because nobody's disproved it yet.
Oh.
Because it's a theory. Boom. All right. So, compressibility refers to how easily something can be pressed together. Compressibility. Now, because particles are so spread apart, they do not repel one another very much if the volume were to decrease. So they're highly compressible. Remember, we're mostly empty space. Right? So if I push down on this piston here, right, my volume goes down, but it doesn't really change much. I'm still a gas. I just took away some of that empty space. Now notice how a decrease in volume, right, so here it was 1 liter, here it is 0.5 liters, is an increase in pressure between 100 kilopascals to 200 kilopascals. So a decrease in volume is an increase in pressure.
Wait, we don't have to do the 2. Okay. How many times do we have to do?
Are we keeping up so far?
Okay.
Okay, so that brings us to our first law. A law does what?
No, it's
Describes, usually from a mathematical equation. Right, so we're about to see an equation.
random moment.
I hate it.
So, effusion. We've talked about diffusion. Right? We said that diffusion, right, was the ability of some, or not really the ability, but the process of something spreading out to fill its container. When you spray perfume, it fills your container, it diffuses. Effusion is similar to diffusion, but it is not the same thing. So this is the movement through a small hole in a container. Right? So that being, if I were to punch a hole in the wall, how quickly could the perfume get through the hole? That would be pretty impressive because this is cinder block, so.
Oh, I got you.
I was gonna say, what would you have to say?
Ah, alright. Alright.
Yeah.
So, Graham's law of effusion says that a gas will effuse at a rate that is inversely proportional to the square root of its molar mass. Which is this. Remember I said that kinetic energy is 1/2 the mass times the velocity squared. So if the mass is bigger, what can I have to say about its velocity? It's smaller. So that's what we see here. When the molar mass of A, right, they're on opposite sides, B is on opposite sides. So the main idea is that small particles with small molar masses move faster. That makes sense, right? We've talked about before, if I had a mouse versus an elephant in this room, which one could probably get to the back door faster? It's gonna be the mouse. The elephant causes
What if the elephant steps on the
all other problems.
Yeah.
What
Well,
if it
you
steps
put
like
an
that?
elephant and a mouse next to each other, elephants will freak out.
Will it really?
Yeah, elephants are afraid of things.
All right. Who tested this?
Why?
It probably was just a byproduct of like the circus where you have lots of elephants and lots of mice.
There's mice at the circus. Wait, why are they scared?
I don't know. Why are we scared of spiders?
I'm
Not everyone's scared of spiders.
Not every elephant's scared of mice. This is so off topic. All right. So let's do an example of this, which should have been.
Wait, are you recording this?
Yeah.
Hey.
Whatever. I'm sure Sierra, Anna, Christian, and Allie will enjoy our
When did
conversation.
they get back?
Were they
Today.
actually watching?
Hi guys. How are you? Yeah. All right.
Oh my gosh.
Okay. So
We love you.
We love you.
here is the example at the bottom of the page. So an unknown gas effuses 1.66 times more rapidly than carbon dioxide. So what is the molar mass of that unknown gas? So the rate of the unknown over the rate of the carbon dioxide, right, is the square root of the molar mass of the carbon dioxide over the molar mass of the unknown, right? So the unknown is what I called A, and the carbon dioxide is what I called B. Now, saying that the unknown gas effuses 1.66 times more rapidly, right? That's basically saying that for every 1 carbon dioxide that gets out, 1.66 of the unknown gas can get out. Does that make sense? If I can effuse 1.66 times more rapidly, for every 1 molecule of carbon dioxide that can get out the hole, right, I can get 1.66 molecules of the unknown gas.
Is that where you got the squared from?
No, we're not talking about the squared yet. I'm just looking at comparing the rates.
You do the squared to get rid of the.
Hold on, we're not there yet. Okay, so that means, all right, looking at the square root of the molar masses, I know the molar mass of carbon dioxide. What's the molar mass of carbon? 12.01. All right, each oxygen is 16. So 16 times 2 is
32.
plus 12.01 is
44.
44.01. Right, that's how I got the molar mass of the carbon dioxide. So the only thing I have left is to calculate the molar mass of the unknown. Now, if I have a square root over all of this, how do I get rid of the square root?
Square it.
You square it.
Oh.
Okay. So this entire side's squared. Right. So this is the same as the square root of this over the square root of that. Right. So you square both sides. This ends up being 1.66 squared. So this is 2.76. Squaring a square root basically just gets rid of the square root. So it's still just 44.01 over the molar mass. Now, this tends to be a big problem when I teach this unit. Right? It's not the chemistry, it's the algebra. Okay? How do I solve for molar mass here? What? You multiply both sides by the molar mass, so that moves molar mass over here. Then you divide by 2.76. So this is 44.01 divided by 2.76, not 2.76 divided by 44.01. That is a big mistake that people make.
Couldn't you just times it? Like times 144.1 and
No.
cancels out?
No, that is not how that works. That would end up being 44.01 squared, which is what it's not what we just did. Okay. So move this to the other side, divide 44.01 by 2.76. Right, you end up getting 15.9 grams per mole. Okay, now I want you to think about this. Yes?
How you know it's grams?
Because it's molar mass.
Okay.
Yeah, not all of it, but most of it. Right, so because it's 1.66 times more rapid than CO2, for every 1 rate of CO2, you have a 1.66 rate for the unknown gas.
Will it always be 1?
Well, if it's 1.66 times more, then yes, it's whatever the rate that you have times over 1.
Well, I would say it's always going to be over 1.
Yes, as long as you set this up right.
Okay.
Say I put CO2 on top here and the unknown on the bottom, I would have had to flip it. So be very careful with that. Okay. So I want you to think about this. If I am effusing more rapidly, if I'm effusing faster, should I have a higher or lower molar mass than the carbon dioxide? It should be lower, right? Because when I'm smaller, I move faster. Is that true? Yes. All right, 15.9 is smaller than 44.01.